Thank you, Karen. Thank you for the invitation. And this is a great honor to present some of the work I've been doing with some of my colleagues. And recently, we got this new project started. So I will tell you a little bit about that. And this is about intelligent systems, which are in the context of transportations. So what do we mean by intelligent transportation systems? You can probably think about some ideas. This video here that outlines some of the features. We have a number of solutions that will be helping cars driving on the road, pedestrians interacting with the cars. Automation will actually enable reduction of energy and also lower the number of trips that one can make, maybe even the time to go from point A to point B. There's a lot of communication structure in these systems, and some of this infrastructure is taking place right now. Maybe some of you are lucky enough to be able to drive some of these vehicles that are internet connected. Last time I rented a car at 2022 had a lot of features. I was surprised to find them there. This is becoming more and more prevalent in our systems. But very importantly, one of the things that we are looking at is trying to have this interaction between systems. Like you see here, two cars. Maybe one is with a driver with some particular interest and another driver with another particular interest, or maybe it's a self-driving vehicle. How do these systems interact? How do we prevent any sort of kind of issues there, and also support it with other systems, like we know these days that we can fly these drones and maybe understand how this could actually help my transportation opportunity and also increase safety in the system. We're working with Toyota Research Institute, and they are developing actually a real-world self-driving vehicle. We're actually doing our part on that as well here at UCSC campus. There will be an announcement coming up in the next few months where we're actually going to show you our actual vehicle for self-driving vehicles. But Toyota actually is doing a great job at getting this out the door, and it's a very collaborative environment. Toyota has a lot of branches, and is partner of many of our projects, in particular the one I mentioned to you. And they're open to research, unlike other companies, right, that are more secretive about it. So we have a great opportunity here. And also with local companies. Many of you probably have seen this. I've been at this place. I've seen this vehicle. It's a beautiful opportunity for research, local Joby aviation opportunities. But as all these vehicles interact with each other, and the people that use them, and the operators, and the infrastructure, we want these systems to be, to some extent, safe and to be resilient, right? So we want these systems to actually, in a systematic way, work with each other and be somewhat safe, right? But you cannot leave that safety just to randomness, like you see right here. Everything is pretty safe, but a little click right there will be somewhat problematic, as you can imagine, right? So the question is, how do we design these systems in a way which most times are based on engineering concepts, and that's where we come from, and many times use mathematics to understand this rigor and create systems that are proven to work, right? And a lot of testing. So that's where, again, we believe that we can make an interesting opportunity in the context of, in particular, ground vehicles, okay? Self-driving vehicles, which all of us are familiar with. And again, I'm one of those that I like to drive my car. I don't like anybody else to drive it. I like to go fast. I like to feel the dynamics. But I know that there are many opportunities there for people to actually get comfort, get efficiency, and also save energy and cost. So what are we looking at in this project that I'd like to introduce you? We are looking at ways to design the system. Here's a vehicle. This is a Toyota vehicle. And what you see right here is that the vehicle will essentially measure the environment. There are a lot of sensors, lidars, range detectors, GPS information. And with that information, which we call the state update, what happened, the vehicle is going to execute some algorithm and going to say, all right, this is my steering wheel, this is my gas, this is how I should navigate next 5 milliseconds, let's say, very short amount of time. And I can keep doing this over and over, okay? But issue we are looking at is situations where the state update occurs sooner, or in other words, the computation takes long, all right? And if you're familiar with the evolution of self-driving vehicles, when I was a postdoc at MIT, we were in this DARPA Grand Challenge of urban vehicles. And what happened is our vehicle would stop at a stop sign and sit there for 5 minutes, right? So we are way beyond that. You've seen Teslas navigating at intersections and negotiating those. But the question is, what happened when you miss a deadline, right? And many of us probably know what happens when we miss a deadline for paper submissions, right? That's not a good thing. Now, when we are looking at vehicles like this form, there are obstacles, and there are pedestrians. So safety is involved. So missing a deadline is not something we can negotiate. That's a non-negotiable. So in this project, we are trying to understand how we can model the hardware and the software in order to co-design them in a way that harmoniously these systems will interact with each other inside the vehicle, okay? So more perhaps at the intersection of applications and control systems, when we look at control systems, we look at a system, in this case a vehicle, as a physical component, and we try to understand what happens when we change the steering wheel or the gas pedal in the vehicle to create a particular trajectory. And that's what we call feedback. So we sample, we update, and the question we want to understand is what happens when this algorithm takes a long time? How can we actually design the hardware and the algorithm in a manner that is jointly to create this synergy and have a co-design, okay? So this is a $7 million project that we just got awarded. Actually, the kickoff project meeting is next Friday, and National Science Foundation is funding this. And this is with my colleague Murat Archak from Berkeley, Ling Fan from University of Pennsylvania, Jonathan Sprinkle from Vanderbilt, Majid Samani from Boulder, and then two colleagues here, UC Santa Cruz, Abhishek Halder in applied mathematics, and Heiner Litz in computer science and engineering. And as you can see here, we have a number of partners that are working with us, including, as I said, Joby Aviation, Toyota, and others as well, including academic institutions. So the project involves quite a bit of research, but also outreach. So our colleague GuhaThakurta is working with us on the science internship program to create the outreach of our research. We're also working with MESA and other programs on campus. And the research project is essentially understand how to model the systems, both the physics and the platform for computing, how to design control algorithms for those, how to actually optimize them in real time, and then how to implement them in real-world platforms. And that's where Toyota Research Institute and Joby Aviation are going to be key partners to do much of this transition. And this project is actually going to fund more than 8 postdocs and 9 PhD students over the course of the 5-year duration of the project in multiple campuses. So we are very excited about this opportunity. And I wanted to mention some of the things that we will see, hopefully, happening over the next 5 years, 5 years from now. Maybe in a talk like this, I will be able to show you a lot of results. But we're looking at very ambitious metrics, how to improve performance computing, how to reduce development time of software, and how to essentially make the performance changes based on adjustments of the platforms and algorithms be somewhat controlled with a 20% gap. But there are a lot of opportunities for new knowledge, a lot of opportunities for reduction of cost and capabilities for the systems. So let me tell you a little bit about the details. Mainly the hardware part, because there are some mathematics here that are not really useful right now. But imagine that you have this large vehicle right here. What we are doing is scaling those vehicles, coming up with miniaturized versions, which we have in our research labs at different institutions, and then testing them. And as you can see here, we are looking at different type of platforms. So this is an aerial platform what we have in my lab. This is a water platform. This is a surface vessel that we have with our partner in Norway. And here are some footage of the things that we're doing so far, some preliminary results, how you can actually navigate. This is my colleague at Vanderbilt with his own vehicle navigating the environment. And one of the features that I like to emphasize is that all of this is open source. And to me, open source is a good source, right? Because we can build from it, unlike many company products that are closed for obvious reasons. But much of what we do is open source. It's going to be in the public domain. And if we have this vehicle that I mentioned on campus, many of our collaborators here on campus will be able to contribute to the development of self-driving vehicles in the future. And there is a lot of computer simulation and analysis of what happens before we even try everything, especially for safety. We don't want to drive these vehicles without understanding very well how they're going to perform. And there's a lot of opportunities for outreach, and that's something that is very exciting. We're actually building a proposal for an NSF research opportunity for undergrads site where students will come from all over the country here to UC Santa Cruz over the summer, about 8 to 10 students, and work with us on these projects for a 10-week period. They will be housed here, they will be paid by NSF, and we'll have an opportunity to contribute to this project, which I think is a beautiful synergy. Just to wrap up, I know I have 2 minutes. What is the merit of this? I already mentioned, to some extent, we are going to come up with new algorithms, new computing architectures that are co-designed for intelligent transportation systems. We expect that there will be a lot of interest from these companies that we mentioned, but also maybe other opportunities that we can collaborate with. So if any idea comes to you, let me know. And there will be, as I said, some mathematical architecture there that is ingrained in what we do, which is control theory. Now, in terms of impact, broader, maybe more of interest to you, if you look at the cost of computing on a car, 41% goes on the computing part. The energy cost, excuse me. The electric energy cost goes mostly on the computer part, and that's critical, so we can reduce that, have an opportunity there. We can also expect reduce carbon footprint by reducing the use of vehicles in general, by making them more efficient. And maybe a long shot, but I looked at this yesterday. Actually, in 2021, the growth for AI fintech was close to 10 million. So the prediction is not too bad. So we are looking at probably at a revenue by 2030, which is close to 150 billions in growth for that industry alone. And we are far from it, and it's an opportunity. So we should be players for that. All right, so with that, I'd like to thank you for the invitation, and I address any questions.